To illustrate that small changes in the data or decisions that you make about the modeling approach can lead to different splits, I'll rerun our model, first making a change to the random number seed, and then to how missing data is handled. For example, when I run the HP split procedure using the seed 12,431 and separately the seed 10,978 in place of the original random number seed, which was 15,531, I get the exact same decision tree, giving me additional confidence in the way that my sample has been grouped. However, when I use the random number seed 19,381 or 34,342, I get a similar but slightly simpler model. My choice of which model to ultimately use really depends on the goal of my analysis. If I'm trying to design a program to prevent regular smoking in adolescents, the unique constellation of variables that are protective against regular smoking may help inform my work. For example, though adolescents who have not used marijuana are generally at very low risk for regular smoking, the larger tree also tells me that in the context of alcohol use, a student's higher grade point average possibly represents further protection against regular smoking. Because we are using observational data here, we of course cannot assume causation. Still, it's exactly these types of studies that allow us to move toward more direct tests of causation with carefully designed experimental interventions that, if successful, will help us better understand the true nature of these relationships. So let me make another small change to the model. Here I'm adding an assign missing option to proc HP split. As I mentioned, the default in SAS is to drop all observations with any missing data. Another option that can be used is called popular. This option specifies that missing values not be dropped, but rather be assigned to the most popular, that is, largest node at each split. By adding this missing data option and running my program, the result is again a similar tree, but this time with new splits on cigarette availability and race. The take-home message from these examples is that it's important to remember that small changes in the data can result in somewhat different or even very different decision trees. To summarize, decision trees are a type of data mining algorithm that can select from among those and their interactions that are most important in determining the target or response variable to be explained. They create segmentations or subgroups in the data by applying a series of simple rules or criteria over and over again, which choose variable constellations that best predict the target variable. In this way, they allow for a data-driven exploration of nonlinear relationships and interactions among many explanatory variables. As we have seen, an advantage of decision trees is that they are easy to interpret and visualize, especially when the tree is small. Tree-based methods also handle large data sets well and can predict both binary categorical target variables, as shown in our example, and also quantitative target variables. However, as we've shown, small changes in the data can lead to different splits, and this can undermine the interpretability of the model. Also, decision trees are not very reproducible on future data, a detail that we'll return to in our next topic, random forests.